In section 5.6, we'll talk about how we label these configurations now. So we've got different configurations. I've got two different molecules I can draw, for example, of 2-butane. I keep coming back to these ones over and over. Now, I need to be able to say, I need to be able to describe which 2-butane I'm talking about. These two are clearly not the same molecule. They're enantiomers of one another. So I need to have a way to describe which stereoisomer I'm talking about. So to do that, I'll start with one of them. I'll start with this one. I'm going to draw in any missing atoms. So I'm going to draw in the hydrogen there at the stereocenter. So this is my stereocenter. So the first thing I need to do is assign priorities. To each group around a stereocenter. And the basic rule for that is that they go by atomic number. So highest atomic number equals first priority. Lowest atomic number will equal the fourth priority. And so quite commonly, hydrogen will be the fourth one. Not always, but quite often. So hydrogen is 4. So I look here, I've got oxygen, carbon, carbon, hydrogen. Oxygen would be 1, hydrogen would be 4. But now at these two positions, I have carbon on both of them. On this one, the next atom out is hydrogen. On this one, the next atom out is carbon. So I keep going out to either side until I find a point of difference. And so since this one has a higher priority at the next position, this gets the 2, and this side gets the 3. So those are my priorities, assigning priorities. So then once priorities are assigned, I need to arrange the molecule with the 4 group pointing back into the paper, dashed wedge, going away from you. Arrange the molecule with the 4 group back, and then draw a line connecting 1 to 2 to 3. So my 4 group is back. Here's 1 to 2 to 3. That's my line. If it's clockwise, we call that molecule R, which stands for rectus. If it's counterclockwise, the configuration of that molecule is S, for sinister. So if I look at my example molecule, 1 to 2 to 3, my 4 group is going back into the board or into the plane of the paper. 1 to 2 to 3 goes clockwise. So this first molecule is R2-butanol. Now if I look at my other one, there's 2 ways of doing this. One is to go through and solve it the same way and draw in your hydrogen. However, once you've solved the first one, if I can look at this one and see, well, this is opposite of the first one. If the first one is R2-butanol, this one must be S2-butanol. Now here's a great use of your ChemDraw for iPad. In ChemDraw for iPad, you can draw all the molecules that you want with stereochemical labeling off. You can try to determine whether that molecule is R or S on your own. Then you can turn the labels back on, and it will tell you whether it's R or S. So it's a great way to practice these, is to use your ChemDraw for iPad to practice on. Now one thing that you may have noticed is that the enantiomers have a change in configuration from R to S. If it changes from R to S, those two are enantiomers. Well, if you have more than one stereocenter, you can do the same sort of thing. So with more than one stereocenter, if I start with a molecule that has 2 stereocenters that are both R, the enantiomer has to have both of them opposite. So the enantiomer would have to be SS. That means that if I have any that only have one changed, RS or SR, those are diastereomers of the original molecules. Now, RS to SR, these two would again be enantiomers because both stereocenters are exactly opposite. So anytime that you have more than one stereocenter, all of the stereocenters need to be completely opposite to be the enantiomer of that molecule. So I'll give you a practice one real quick without even drawing the molecule. If I have a molecule that is RSS stereochemistry, what would the enantiomer be? Hopefully you figure out that it would be SRR. That would be the enantiomer. Any other changes, RRR, RRS, RSR, any other change except for SRR are all diastereomers. Now I hope that you remember that I talked about before that if I have two or more stereocenters, my molecule may or may not be chiral. And the reason it has to do with planes of symmetry. So here's a molecule that has two stereocenters. If I look at this top one, I've got 4 different groups. I've got a hydrogen going back. I've got an OH. Down to this side, I have a C with O. To this side, I only have a C with another C. So these are different. And this is the stereocenter too. So these two are both stereocenters. However, there's a plane of symmetry right through there, through that molecule. Everything on the top is an exact reflection of everything on the bottom. And so because there's a plane of symmetry, this molecule has to be achiral. So in section 5.8, it addresses that, and we call these compounds mesocompounds. Compounds that are meso have stereocenters, but they're achiral due to a plane of symmetry.